Around 4.5 billion years ago, Earth was still a newborn planet, an incandescent body forged from the leftover cosmic dust and debris following the formation of the Sun. Gravity pulled these particles together through violent collisions, causing the planet to grow in both mass and heat. This intense heat, combined with the residual energy from colossal impacts and the radioactive decay of heavy elements, led to the internal differentiation of the Earth. Denser materials like iron and nickel sank to form the core, while lighter elements rose, giving rise to the mantle and crust. Thus were born the planet's first geological layers, each with distinct properties and functions. The thin, irregular crust became the stage for future surface transformations, while the thick and viscous mantle slowly moved under intense pressures, enabling continental drift and the recycling of crust through plate tectonics. As Earth's surface began to cool, the first ocean basins formed, and over time the earliest continental masses began to consolidate. Solar winds and asteroid bombardments diminished, and the primitive atmosphere, once toxic and composed of carbon dioxide, methane, and ammonia, started to change. It was in this still hostile environment that the first rains fell, cooling the ground and filling low-lying areas with water. During this time, the planet recorded its first sedimentary cycles. Rock debris and organic particles were carried by primitive rivers and deposited on ocean beds, forming layer upon layer of sediment. These sedimentary basins, under the pressure of millions of years, became subterranean vaults of organic matter that would one day give rise to fossil fuels. But to understand how coal, oil, and natural gas form, it's essential to grasp the vital role of microscopic life and ancient vegetation in creating these reserves. During the Paleozoic and Mesozoic eras, vast forests covered large regions of the planet, composed of giant ferns, lycophytes, ancestral conifers, and pteridophytes. When these plants died, they accumulated in oxygen-poor wetlands, which prevented the complete decomposition of plant material. Over time, these vegetative layers were buried under sediments, slowly compressed and heated by geological processes spanning tens of millions of years. Layer by layer, mineral coal deposits were formed primarily during the Carboniferous period between 360 and 300 million years ago. In marine environments, a similar process occurred, but it involved the accumulation of plankton, microscopic algae, and the remains of marine organisms. These remains sank and settled in anoxic ocean floors, where decomposition was partial, and the organic material was preserved in the form of carbon-rich mud. Over millions of years, the continuous burial, combined with increasing pressure and temperature, transformed this mud into kerogen, a precursor to oil and natural gas. As kerogen was pushed to greater depths under extreme heat and pressure, liquid and gaseous hydrocarbons began to form and migrate through porous rocks until they were trapped beneath impermeable layers, creating what we know as reservoirs. This geological process is so slow and demanding that a single liter of oil can take up to 300 million years to form. The creation of these resources requires a precise balance between the rate of organic deposition, the absence of oxygen, the type of sediment, and the thermal conditions of the basin. That's why the world's largest oil and gas reserves are concentrated in just a few regions that, in the distant past, met these specific conditions, such as the Middle East, the Gulf of Mexico, the Amazon basin, the Caspian Sea, and western Siberia. Each of these areas holds deep within the earth the mineral memory of forgotten ages, preserved in rocks that were once seas, forests, swamps, or deserts. These formations not only tell the story of Earth, but also reveal the complexity of our modern dependence. After all, the energy that powers cars, factories, and cities did not appear overnight. It is the result of a patient, blind geological process indifferent to human urgency. What we now extract with drills and explosions was once life. Life that transformed into energy over incomprehensibly long cycles. And while humanity seeks to accelerate its pace of production and consumption, natural processes remain unchanged, reminding us that nature does not work in haste, but with precision. To truly understand the nature of coal, oil, and natural gas, we must dive into a time far beyond human perception, a geological time measured not in years or centuries, but in millions of years. Fossil fuels are not merely resources, they are fossilized legacies of life itself. Every carbon particle stored within them carries the memory of an organism that once breathed, grew, or floated in ancient oceans. Over the ages, these life forms died and settled into Earth's sediments, slowly transformed, compressed, and baked within the planet's interior under colossal pressure and intense heat. It is this deep, silent, and prolonged cycle that turns dead life into stored energy. Coal originates mainly from the wet, dense forests that blanketed vast areas of the Earth during the Carboniferous period, between 360 and 300 million years ago. At that time, there were no dinosaurs or large mammals, but the atmosphere was rich in oxygen and the climate was warm and humid. Giant ferns, mosses, horsetails, and primitive trees up to 30 meters tall thrived in swampy wetlands, where stagnant water prevented the complete decomposition of organic material. When these plants died, they formed thick layers of peat, a partially decomposed organic substance. Over time, this peat was buried by sediments, and the increasing pressure and underground heat gradually turned it into coal. First into lignite, then into bituminous coal, and under more extreme conditions, into anthracite, the purest and most energy-rich type of coal. Each stage represents a greater degree of carbonization, meaning a higher carbon content and therefore a higher heat value. Oil, in contrast, is born mainly in marine environments from carbon-rich mud composed of plankton, algae, and microscopic remains of marine organisms that accumulated in ancient shallow seas and deep ocean basins. This material, known as organic matter, was deposited alongside clay particles and fine sediments. In anoxic environments, low in oxygen, decomposition was halted and the organic mud was preserved. Over time, continuous burial increased the pressure and temperature, initiating the slow transformation of organic matter into kerogen, a solid substance that bridges the gap between living material and hydrocarbons. Kerogen is the embryo of oil. As the source rock is buried deeper and heated between 60 and 120 degrees Celsius, liquid hydrocarbons separate from the kerogen, migrating upward through porous rocks until they become trapped beneath impermeable formations, forming oil reservoirs. Natural gas can form in association with oil, called associated gas, or independently through similar processes, but under even higher temperatures, between 120 and 200 degrees Celsius. Within this thermal range, known as the gas window, organic molecules break down even further, producing lighter and more volatile hydrocarbons. Methane is the primary component of natural gas, but it may also contain ethane, propane, butane, and other compounds. Gas is often found in the same sedimentary basins as oil, but at deeper levels or within specific geological traps. The formation of an oil field or gas deposit requires 4 fundamental geological elements: a source rock rich in organic matter, a reservoir rock porous enough to store the fluid, a sealing rock that is impermeable to prevent hydrocarbons from escaping, and a geological trap, such as a fold, a fault, or a salt dome, capable of enclosing the oil or gas within a defined space. Without these 4 elements, oil may have formed, but it would have escaped to the surface, dissipated or oxidized over time. These fossil fuels remain trapped for tens or even hundreds of millions of years until human action uncovers them. But this process is far from simple. It requires cutting-edge technology, deep knowledge of local geology, advanced drilling equipment, and enormous financial investments. Every drilled well is a gamble, a shot at accessing ancient time buried beneath our feet. Some drilling attempts yield nothing, while others reveal vast reserves that reshape the fate of entire nations. It is a game of patience and precision, built upon seismic studies, computer modeling, and geochemical data gathered over decades of research. Behind the comfort of the energy that heats our homes, powers our vehicles, or fuels our industries, lies an almost invisible natural process that occurred when dinosaurs still roamed the earth, or even earlier. Every drop of oil, every cubic meter of gas, every chunk of coal represents the end of a long chain of natural events that turned life into fuel. Using these resources, therefore, is burning history. It is releasing, in mere seconds, energy that took millions of years to accumulate. And this unbalanced relationship between natural time and human consumption lies at the core of the energy and environmental crisis we face today. Long before humans became familiar with fossil fuels, their relationship with energy was direct, visible, and organic. Survival itself depended on the ability to harness and conserve primitive sources of energy: sunlight, wind, flowing water, and especially the biomass available in the surroundings: wood, dry plants, animal dung, and muscular strength. The domestication of fire around 1.5 million years ago marked the beginning of this energetic journey. Fire allowed Homo erectus to cook food, stay warm in harsh climates, and keep predators at bay, opening a new chapter in human survival. Though rudimentary, this discovery was the species' first energy leap, establishing a permanent link between civilization and energy. Over time, as humans evolved, so did their methods of capturing and transforming energy from their environment. In the Neolithic era, about 10,000 years ago, with the rise of agriculture and animal domestication, muscle power became central. Oxen plowed fields, horses carried loads, and human labor was distributed more efficiently. Ancient civilizations, such as those in Egypt, Mesopotamia, China, and the Indus Valley, built irrigation canals, stored rainwater, and used gravity to their advantage. Even on a small scale, water power began to be used to turn wheels and grind grain, a primitive but effective way of converting potential energy into mechanical work. Greece and Rome expanded on this knowledge. The Romans, for instance, used water wheels to operate mills, hammers, and saws. In ancient China, wind power was used to pump water through windmills centuries before its widespread adoption in Europe. Wood was the primary source of heat and fuel throughout the ancient world, and entire forests were cut down to feed ceramic kilns, public bath boilers, and metal forges. Energy was still local, limited to human and animal labor and natural elements, but it was already capable of drastically altering the surrounding environment. During the Middle Ages, the use of watermills and windmills spread across Europe, providing mechanical energy for daily tasks. Mills ground grain, presses extracted oils, saws cut timber, and bellows powered forges. In flat regions where rivers were scarce, wind took center stage. And although these energy sources were simple, they were relatively sustainable, as they relied on natural and renewable cycles. This reality only began to change dramatically with the arrival of the 18th century and the Industrial Revolution. The turning point came with the realization that coal, until then used sporadically as a fuel, could provide heat and energy far more intensely and consistently than wood. When the first engineers like Thomas Newcomen and later James Watt developed efficient steam engines, humanity discovered that coal's heat could generate movement, and with it, automate labor. Locomotives, ships, factories, and mines began to run on energy extracted from Earth's depths, initiating a new energy era, the fossil fuel era. From that moment on, energy ceased to be a natural phenomenon and became a commodity. With coal powering the engines of the Industrial Revolution, modern cities emerged, mass production systems were born, and new standards of living were established. But so too came clouds of smoke, polluted rivers, and a vicious cycle of extraction, consumption, and waste. Energy, once slowly harvested from nature, was now torn from the earth by the ton and burned in seconds, with little or no environmental control. The scale of human activity changed, and with it, the pressure on the planet intensified. This energy leap was an undeniable advancement for civilization, but it set humanity on a path of imbalance. The abundance of energy from coal, and later from oil and gas, created a sense of energetic independence. Yet this energy still depended on lengthy natural processes that humans cannot replicate in a lab or produce at geological timescales. That means even with turbines, engines, and refineries, we remain bound to nature's logic. We consume in days what took ages to form. And this deeply unequal energy equation lies at the heart of the environmental collapse that looms before us. The discovery of oil as an energy resource would mark not just a new chapter in human history, but the beginning of an irreversible transformation in how the world operated. Before oil, coal was the undisputed king of energy, dark, dense, efficient, but heavy and difficult to transport. Oil, on the other hand, appeared as a viscous, flammable, and abundant liquid, capable of generating enormous amounts of energy in small volumes and with far greater versatility. Its rise was not immediate, but once it gained attention, it became the engine of modernity, fueling wars, shaping economies, and completely redrawing the global balance of power. Oil had been known since antiquity. Civilizations such as the Sumerians, Assyrians, and Egyptians used bitumen, a semi-solid natural form of petroleum, to waterproof boats, seal buildings, and embalm bodies. However, it was only in the 19th century that oil began to be systematically extracted. The turning point came in 1859, when Edwin Drake drilled the first commercial oil well in Pennsylvania, United States. From that moment, the oil industry took shape. Initially, its primary use was as kerosene, replacing whale oil in public lighting. But what followed would turn this dark liquid into the lifeblood of the 20th century. With the invention of the internal combustion engine, and later the advent of the automobile by Carl Benz and Henry Ford, oil began to be refined into gasoline and diesel, revolutionizing transportation. Soon, fossil fuel was powering cars, trucks, ships, airplanes, and even war machines. The First World War was already a war powered by oil, but it was the Second World War that demonstrated its global strategic importance. Entire armies were immobilized due to fuel shortages, and battles were fought over supply routes and oil fields. Energy became, quite literally, a matter of life or death among nations. The rising demand triggered a frantic search for new reserves. Countries like Saudi Arabia, Iran, Iraq, Kuwait, and Venezuela emerged as major producers, while large Western companies, known as the Seven Sisters, began to control global operations. The discovery of vast oil fields in the Middle East turned desert regions into geopolitical powerhouses. Cities like Riyadh, Dubai, and Doha rose almost out of nowhere, fueled by petrodollars. Meanwhile, oil became the invisible pillar of modern civilization. It not only powered engines, but also became the base for the production of plastics, fertilizers, pharmaceuticals, cosmetics, and countless everyday products. Starting in the 1970s, the world began to realize that oil dependency also carried enormous risks. The 1973 oil crisis, triggered by an Arab embargo, exposed the vulnerability of Western economies. Long lines at gas stations, runaway inflation, and economic recessions showed that oil was not just a commodity, it was a raw nerve of civilization. This awareness led to the creation of the International Energy Agency and initiatives for energy conservation. Yet, global consumption did not slow. Oil became so essential that any attempt to replace it was met with skepticism, or seen as an economic threat. The geopolitics of oil shaped the 20th century with rare intensity. Wars such as the Gulf War, military invasions, coups d'etat, and international alliances were directly or indirectly driven by competition over this resource. Control over pipelines, refineries, and export routes became more valuable than diplomatic treaties. OPEC, Organization of the Petroleum Exporting Countries, began setting production quotas and prices, influencing markets and monetary policies around the globe. Oil ceased to be merely a source of energy. It became the axis around which public policies, international relations, and even the planet's climate future revolved. Over the decades, the oil industry grew more sophisticated. Technologies like horizontal drilling, 3D seismic imaging, offshore platforms, and hydraulic fracturing, fracking, allowed access to previously unreachable fields. Countries like Brazil, Canada, and Norway rose as major deep-water producers. The United States, through shale oil, regained energy self-sufficiency. But all this expansion came at a heavy environmental cost. Oil spills, such as the Exxon Valdez disaster in 1989 or the Deepwater Horizon catastrophe in 2010, revealed the ecological risks of energy dependence based on relentless extraction. The discovery of oil didn't just move the world, it shaped it. Our consumption habits, urban expansion, globalization, industrialized food systems, and even modern armed conflicts are tied to the logic of oil. It's in our tires, our clothing, our packaging, and our computers. The modern world as we know it is quite literally built on it, and that's the paradox. The more we advance with oil, the further we drift from a balanced relationship with the planet. Among the three main fossil fuels, coal, oil, and natural gas, it is gas that carries the reputation of being the cleanest of the trio. This image, though partially true, hides complex layers regarding its origin, environmental impact, and its role in the global energy transition. Natural gas is essentially a mixture of light hydrocarbons, with methane, CH4, as its main component. It forms through the thermal decomposition of buried organic matter, typically within the same sedimentary basins as oil, but under higher temperature conditions. Its molecular structure allows for more efficient combustion with lower carbon dioxide emissions than coal or oil, which has led many countries to view it as an energy bridge between fossil fuels and a future based on renewables. Natural gas forms in much the same way as oil, but its generation window occurs at temperatures between 120 and 200 degrees Celsius, placing it in deeper layers of the Earth's crust. It may be found associated with oil, either dissolved or as a gas cap atop reservoirs, or independently in purely gaseous fields. It can also occur in unconventional formations, such as shale gas, trapped in low permeability rocks that require techniques like hydraulic fracturing for extraction. There is also coalbed methane, found in deep coal mines and associated with carbonized organic matter. From an environmental standpoint, natural gas emits about 50% less carbon dioxide than coal and 30% less than oil per unit of energy produced. This has given it space in countries seeking to reduce emissions without entirely abandoning fossil fuels. Natural gas-fired power plants have been seen as less dirty substitutes for old coal plants. Additionally, gas allows for rapid adjustment of energy supply, making it useful for complementing intermittent sources like solar and wind. Its combustion also produces less particulate matter, sulfur oxides and mercury, which translates into better air quality and public health benefits. However, methane, the primary component of natural gas, is a highly potent greenhouse gas with a global warming potential roughly 80 times greater than that of carbon dioxide over a 20-year period. Small leaks throughout the production, transportation, and distribution chain can cancel out the environmental benefits of cleaner combustion. These leaks, known as fugitive emissions, are difficult to detect and control, especially in regions with poor infrastructure or weak regulation. Modern satellites and sensors have revealed that real methane emissions from the gas industry are much higher than previously estimated, casting doubt on its supposed cleanliness. Moreover, the infrastructure required to extract, process, and transport natural gas is highly capital and energy intensive. Intercontinental pipelines, liquefaction terminals, LNG, methane tankers, and urban distribution networks demand massive investments and technical complexity. Producing countries like Russia, Qatar, Algeria, and the United States export gas through global networks often fraught with geopolitical disputes. Natural gas, therefore, is subject to the same strategic risks as oil, including sanctions, supply cuts, and price shocks that directly affect populations and entire economies. In recent years, natural gas has been promoted as a temporary solution to the energy and climate crisis. Its operational flexibility makes it ideal for use alongside renewables, balancing fluctuations in supply and demand. However, this bridge position has been criticized by environmentalists and climate scientists who warn that this transitional phase may become permanent, locking in investments in fossil infrastructure and delaying the shift toward truly clean energy. Large gas projects have lifespans of decades, and once built they are rarely abandoned before they are financially amortized. Despite these challenges, natural gas continues to expand. It is used for electricity generation, residential heating, as a feedstock in the chemical industry, and in hydrogen production. It is also compressed and used as vehicle fuel, particularly for urban fleets. Developing countries see it as a cheaper and less polluting option than coal, while wealthy nations use it to reinforce energy security. But the crucial question remains: should natural gas be seen as a stepping stone toward clean energy, or as the foundation of a rebranded fossil economy? The answer depends on how it is used and for how long. If it serves as a transitional phase with clear targets, strict oversight and effective emission controls, it may help reduce global emissions in the short term. But if treated as a final solution, we risk keeping humanity trapped in an extractive, carbon-intensive logic that drifts ever further from a sustainable relationship with the planet. Gas may be cleaner than its fossil siblings, but that doesn't make it inherently clean. It must be viewed with critical eyes, aware of its benefits but also of its limitations. To understand why coal, oil, and natural gas are concentrated in specific regions of the planet and not in others, it's necessary to dive into the silent language of geology. These resources are not randomly distributed. Their presence depends on a rare and specific combination of geological factors, each one an essential piece of a subterranean puzzle that took hundreds of millions of years to assemble. Locating, mapping, and extracting an energy field requires deep knowledge of Earth's history, its layers, faults, depositional cycles, and tectonic movements. In this context, geology is both a guide and a gatekeeper of the planet's energy secrets. The formation of an oil or gas reservoir requires at least 4 key geological elements: a source rock, a reservoir rock, a seal rock, and a structural or stratigraphic trap. The source rock is rich in organic matter, usually a black marine mud deposited in anoxic environments, which was buried and thermally matured to generate hydrocarbons. The reservoir rock, such as sandstone or limestone, is porous and permeable, capable of storing those hydrocarbons. The seal rock is an impermeable layer, like shale or salt, that prevents oil and gas from migrating to the surface. The trap is the geological structure that confines the fluid in a defined space, forming what is known as an oil or gas field. There are different types of geological traps. Structural traps result from tectonic deformations, such as anticlines, convex rock folds that act as natural vaults, or faults that create displacements and barriers. Stratigraphic traps occur due to variations in sediment deposition, such as inclined layers, sandstone lenses, and unconformities. In both cases, the combination of hydrocarbon presence, sufficient porosity, and effective sealing determines the potential of an energy field. If any of these elements is missing or imperfect, the hydrocarbons may have escaped or never accumulated at all. Modern technology enables geologists and engineers to explore these structures with precision. Three-dimensional seismic reflection is one of the main geophysical tools used today. In this method, sound waves are artificially generated and sent into the subsurface. These waves reflect off rock layers and return to the surface, where sensors record them. These data are used to create detailed 3D models of the subsurface, revealing faults, domes, and potential traps. In complex regions like thick salt basins, such as Brazil's pre-salt, advanced seismic processing and artificial intelligence are used to reduce uncertainty and improve drilling success. Exploration also requires geochemical knowledge to identify oil and gas indicators in surface rocks or deep core samples. Thermal maturity analysis, total organic carbon (TOC) content, and isotopic composition help determine whether a rock can generate hydrocarbons. Petrophysics studies the properties of reservoir rocks, such as porosity, permeability, and fluid saturation. All this data is integrated into geological and economic models to estimate recoverable volumes and evaluate project feasibility. The world's great petroleum provinces are the result of unique geological histories. The Middle East, for example, holds enormous fields due to the tectonic stability of the Arabian platform and the continuous deposition of organic matter in shallow seas during the Mesozoic era. Western Siberia has a thick sequence of sedimentary rocks with multiple overlapping petroleum systems. The North Sea, Brazil's Santos Basin, the Caspian region, and the Gulf of Mexico also present ideal conditions for major field formation. In these areas, the combination of mature source rocks, high-quality reservoirs, and effective seals has created true energy vaults. Coal, in contrast, forms in continental basins where vast prehistoric forests were buried. These basins are usually associated with ancient subsidence zones, areas where the crust slowly sank and accumulated organic sediments. The world's main coal deposits are found in the United States, Appalachians, China, Shanxi, Russia, Kuzbass, Australia, Bowen Basin, and India, Jharia. Each of these regions contains fossilized remnants of vegetation that once covered the Earth over 300 million years ago. Beyond revealing where fossil fuels lie, geology also helps us understand the risks of extraction. Tectonically active regions like Iran or Indonesia present additional challenges such as earthquakes and reservoir instability. Offshore areas require floating or fixed platforms anchored hundreds of meters deep. Unconventional reserves like shale gas require horizontal drilling and hydraulic fracturing, techniques that carry risks of groundwater contamination and methane emissions. Geological science is therefore essential to modern energy. It shows us that fossil fuels are the result of rare, delicate, and unrepeatable geological coincidences. They are gifts from Earth, stored in deep vaults that only open when we understand their mechanisms with humility and precision. And at the same time, it reminds us that every extraction comes with a cost, and when that cost is ignored, it demands payment in the form of environmental imbalance, social instability, and resource depletion. The journey of a fossil fuel from its geological cradle to its final combustion is long, complex, and marked by a global chain of monumental infrastructure. From deep within Earth's crust to the tank of a car, or the flame of a thermal power plant, every molecule of oil, natural gas, or coal follows a path carefully orchestrated by technical, logistical, and financial networks. The infrastructure that supports this invisible energy system is everywhere, beneath our feet, crossing oceans, running along rails, buried underground, and even in the air. It is one of the largest engineering systems ever built by humanity, and also one of the most delicately interdependent. Let's begin with oil. Once an oil field is discovered and deemed economically viable, the construction of the extraction system begins. This may include hundreds of interconnected wells, production platforms, separation units, and initial storage facilities. On shore, this process involves pump jacks, internal pipelines, and compression stations. In offshore environments, like Brazil's pre-salt fields or those in the North Sea, floating or fixed platforms are installed at sea, connected to sub-sea pipelines that carry the oil to offloading ships or the mainland. These structures operate 24 hours a day, with millimetric precision and a high degree of automation. Once extracted, crude oil must be transported to refineries, where it is converted into usable products like gasoline, diesel, kerosene, asphalt, lubricating oil, plastics, and hundreds of derivatives. This transport is done via pipelines, enormous underground or underwater tubes that cross entire continents, or via oil tankers, which are floating cities capable of carrying up to 2 million barrels at a time. Pipelines like the Keystone in the US. The Druzhba in Russia and the Trans-Arabian in the Middle East are examples of energy arteries that traverse vast geographies, often crossing political borders and zones of geopolitical tension. Refineries are highly sophisticated industrial complexes with thermal units, fractional distillation towers, catalytic cracking processes, and hydrotreatment systems. Crude oil is heated and separated into different fractions based on boiling points. Each fraction is routed to specific units, where it is transformed into final or intermediate products. The efficiency of a refinery is measured by its ability to crack larger molecules into smaller, more valuable compounds. After refining, fuels are transported again, this time via tanker trucks, rail cars, ships, or smaller pipelines to gas stations, airports, factories, and end users. Natural gas, in turn, relies on another complex network. Once extracted, it must be processed to remove impurities like water vapor, carbon dioxide, sulfur compounds, and other liquid hydrocarbons. Only then can it be compressed and injected into pipeline systems or liquefied at cryogenic temperatures, -162 degrees Celsius, to be transported as LNG, liquefied natural gas. LNG is stored in specially designed methane carriers that deliver it to regasification terminals in other countries, where it is converted back to gas and fed into distribution networks. Japan, South Korea, and several European Union nations rely heavily on this liquid energy route. Coal infrastructure is more visible but no less robust. After being mined, coal is crushed, sorted, and stored in silos or open-air stockpiles. It is then transported, usually by rail or bulk carrier ships, to thermal power plants. These plants burn coal to heat boilers, produce steam, and spin turbines that generate electricity. Countries like China, India, Australia, South Africa, and the United States maintain vast railway and port networks dedicated exclusively to coal transportation. Some regions operate export terminals capable of shipping tens of millions of tons per year. All these systems, pipelines, gas networks, refineries, ports, platforms, ships and power plants, require constant maintenance, environmental monitoring, safety protocols, and significant capital. Any failure in a single link of the chain can lead to devastating consequences. Leaks, explosions, mechanical breakdowns, or natural disasters can compromise supply, cause ecological damage, and spark political or economic crises. The Texas City refinery explosion, the Colonial Pipeline spill, and California's energy blackout are examples of how mismanaged infrastructure can become a catastrophe. Moreover, this global infrastructure sustains a quiet dependency. Even as we sleep, thousands of ships cross oceans carrying oil, underground pipelines pump gas at hundreds of kilometers per hour, and power plants burn coal to keep lights on and machines running. Modern life is deeply entangled in this system, almost invisibly yet pervasively. Every click on a computer, every refrigerated meal, every plane taking off depends on this hidden machinery. The world as we know it could not function without it, and it is precisely this structural dependence that makes the transition to cleaner, more sustainable energy so difficult. The infrastructure that moves fossil fuels across the planet is both a technological marvel and a silent source of ecological imbalance. For more than a century, the benefits brought by abundant and cheap energy seemed undeniable. Illuminated cities, rapid transportation, expanding industries, and improved quality of life. However, as the decades passed, an environmental debt began to accumulate quietly, and today it has become impossible to ignore. Fossil fuels, through their extraction, transport, and consumption, release a massive load of pollutants into the soil, water, and atmosphere. More than that, they disrupt the planet's climate balance, destabilizing millennia-old cycles and threatening the systems that sustain life as we know it. Air pollution is one of the most visible and deadly consequences of unchecked use of coal, oil, and gas. Burning these fuels in power plants, vehicles, and industries releases large volumes of sulfur dioxide, SO2, nitrogen oxides, NOx, particulate matter, PM2.5 and PM10, and volatile organic compounds, VOCs. These pollutants not only make the air unbreathable in many cities, but also penetrate deep into the lungs, worsening respiratory, cardiovascular, and neurological diseases. According to estimates by the World Health Organization, air pollution kills around 7 million people each year, directly or indirectly, a staggering number often underestimated by the global public. Meanwhile, the soil and water suffer the collateral damage of extraction and transport. Open-pit coal mining reshapes entire landscapes, destroys ecosystems, and contaminates groundwater with heavy metals and toxic waste. In the case of oil, spills and leaks remain a constant threat. The 1989 Exxon Valdez disaster, which dumped nearly 40 million liters of crude oil into Alaskan waters, destroyed marine ecosystems for decades. The Deepwater Horizon spill in the Gulf of Mexico in 2010 was even worse. 780 million liters of oil were released into the ocean over several months, killing fish, birds, corals, and permanently altering regional life cycles. These events are not exceptions. They are symptoms of a system where risk is embedded in the operation. Even under normal conditions, fossil fuel use releases billions of tons of carbon dioxide, CO2, and methane, CH4, into the atmosphere each year. These greenhouse gases accumulate like an invisible blanket around the Earth, trapping solar radiation that should be escaping into space. The result is global warming, a slow but cumulative process that has already raised the planet's average temperature by more than 1 degree Celsius since the Industrial Revolution. That may seem small, but it shifts rainfall patterns, intensifies heat waves, accelerates polar ice melt, raises sea levels, and triggers increasingly frequent extreme weather events. The melting of Arctic and Antarctic ice, for instance, is not just symbolic. It changes Earth's albedo, its ability to reflect sunlight, worsens warming and threatens both human and animal populations. Polar bears, seals, and seabirds lose their habitats, while coastal nations face seawater intrusion, aquifer salinization, and erosion of fertile land. In tropical regions, cyclones grow stronger, droughts last longer, and floods become more destructive. Ecosystems such as the Amazon rainforest, the Great Barrier Reef, and the Himalayan glaciers are under pressure, threatened by changes that began with the silent burning of coal and oil thousands of kilometers away. Another, less visible but equally devastating impact is ocean acidification. Carbon dioxide that doesn't remain in the atmosphere is absorbed by the seas, altering water pH and making it harder for shells, coral skeletons, and other calcium-based structures to form. Entire reefs are bleaching and dying at alarming rates. Marine life, responsible for a large share of the oxygen we breathe, is silently being eroded by the industrial expansion powered by fossil fuels. And as if that weren't enough, plastic, also derived from oil, floods rivers, beaches, and deep ocean trenches, poisoning animals, entering the food chain, and even returning to our own plates. It's important to understand that these are not merely environmental consequences. They are human, economic, and social crises. Vulnerable populations, often poor and marginalized, are the ones most affected by climate disasters, health crises, and environmental collapse. Pollution kills quietly in peripheral neighborhoods, while climate change displaces entire communities, creating environmental refugees who join the ranks of those displaced by war and hunger. The climate crisis, fueled by fossil fuels, is also a crisis of justice, equity, and survival. Science is clear. If we do not drastically reduce the use of fossil fuels in the coming decades, the impacts will become irreversible. And with each year lost, the window for action narrows. The planet doesn't demand perfection, only action. The energy transition, consumption efficiency, renewable sources, reforestation, education, and global cooperation are all tools we already possess. The question is whether we will have the courage to use them before the cost of inaction becomes unbearable. Global warming is not a distant forecast or an academic hypothesis. It is a measurable, documented, and ongoing reality. It is the direct result of the imbalance caused by the continuous release of greenhouse gases into the atmosphere, primarily carbon dioxide, CO2, and methane, CH4, mostly from the burning of coal, oil, and natural gas. These gases, though invisible, form a thermal barrier that traps part of the solar radiation reflected by Earth's surface. On a planet without an atmosphere, this radiation would escape into space. But on Earth, the excess of greenhouse gases prevents this dissipation, creating a cumulative warming effect. Since the beginning of the Industrial Revolution, atmospheric CO2 concentrations have risen from about 280 parts per million to over 420, a level never before recorded in hundreds of thousands of years of natural climate records. This warming is neither uniform nor limited to the global average temperature. It profoundly affects the planet's climate systems, altering ocean currents, shifting precipitation patterns, weakening cold air masses, and intensifying extreme weather events. Storms that used to occur once a century now strike every decade. Prolonged droughts hit traditionally fertile regions. Floods destroy entire cities within hours. Melting at the polar ice caps and continental glaciers not only raises sea levels, but also disrupts the Earth's albedo balance, which regulates the absorption of solar heat. Less ice means a darker surface, one that absorbs more heat, fueling a vicious feedback loop. Methane, though less abundant than carbon dioxide, is even more dangerous in the short term. With a global warming potential nearly 80 times greater than CO2 over a 20-year period, it is released by gas pipeline leaks, oil extraction, intensive livestock farming, and the decomposition of organic waste in landfills. Combined with aerosols and suspended particles, this mix of pollutants alters the global atmospheric composition. Satellites like Sentinel-5P and OCO2 track this data in real time, revealing invisible clouds of gas over industrial zones, extraction fields, and megacities. One of the most alarming effects of global warming is the acceleration of the hydrological cycle. With more heat, more water evaporates from oceans, lakes, and soil. This intensifies torrential rainfall in some regions and worsens desertification in others. The result is a climate that is more extreme, less predictable, and more hostile to agriculture, biodiversity, and human life. Traditional crops lose productivity, entire ecosystems collapse, and tropical diseases spread into previously cold regions. Global warming, therefore, is not merely a climate challenge, it is a systemic threat to food security, public health, and social stability. The oceans, which absorb more than 90% of the heat accumulated by the greenhouse effect, also suffer severe consequences. Rising sea temperatures disrupt fish reproduction and migration, destroy coral reefs, and reduce dissolved oxygen, leading to the formation of dead zones. Acidification, caused by the absorption of excess CO2, harms calcifying marine organisms like oysters, corals, and plankton that are essential to the aquatic food chain. Meanwhile, sea level rise, driven by glacier melt and thermal expansion of water, threatens to submerge coastal cities, archipelagos, and river deltas, putting millions at risk of forced displacement. Climate change, driven by fossil fuels, also brings devastating social impacts. Indigenous and rural communities which depend directly on natural balance are the first to suffer. Poor urban populations, exposed to floods, extreme heat, and resource shortages, face growing vulnerabilities. So-called climate refugees, those forced to leave their lands due to extreme events or chronic environmental degradation, are already a reality in several parts of the world. The climate crisis worsens existing inequalities, widening the gap between rich and poor countries, between those who emit the most and those who suffer the most. Several international agreements attempt to confront this scenario. The Kyoto Protocol, signed in 1997, was an initial effort to limit global emissions, but had limited impact. The Paris Agreement, signed in 2015 by nearly every country in the world, established ambitious goals to limit warming to no more than 2 degrees Celsius, with efforts to stay below 1.5. To achieve this, global emissions must be halved by 2030 and reach net zero by 2050. These targets, however, demand an unprecedented energy transition, something that will not happen without political will, massive investment, technological innovation, and deep cultural shifts. Science is unanimous. Over 99% of peer-reviewed studies agree that global warming is real underway and caused primarily by human activity, especially the intensive use of fossil fuels. Ignoring this consensus doesn't change the facts. Earth responds to every ton of carbon emitted, every forest destroyed, every well drilled, with unmistakable signs of imbalance. We are at a crossroads in history. Either we drastically reduce our dependence on coal, oil, and gas, or we will face a century of climate catastrophes, resource conflicts, mass extinctions, and irreversible loss of quality of life. The role of fossil fuels in global warming is not incidental, it is central. And recognizing that reality is the first step toward action. The choice is collective, but the consequences inevitably will be universal. Despite climate warnings, technological innovations, and the growing urgency to decarbonize the economy, humanity remains deeply dependent on oil and natural gas. This dependence goes beyond energy. It is structural, economic, political, and cultural. It is not merely a matter of convenience, but a complex system built over more than a century, involving all sectors of society. Oil, for example, does not just power vehicles. It drives entire logistical chains, fuels petrochemical industries, and serves as the basis for fertilizers, plastics, medicines, and cleaning products. Natural gas, in turn, heats homes, cooks food, generates electricity, and is a vital raw material for hydrogen and ammonia industries. Modern life, in its most basic and invisible form, rests on a fossil foundation. One of the main reasons for this persistence is the existing infrastructure. The world was built on fossil fuels. Oil refineries, gas pipeline networks, thermal power plants, gas stations, truck fleets, airplanes and ships, all were designed to run on carbon combustion. Replacing this structure requires a monumental effort and, above all, time. And while the transition is incomplete, demand for oil and gas remains high. Even in countries investing heavily in renewable energy, such as Germany, Japan, and the United States, natural gas consumption has increased in recent decades as a less polluting alternative to coal. In aviation and maritime transport, for instance, there are still no scalable commercial solutions that match fossil fuels in energy density and technical viability. The global economy is also deeply tied to oil and gas. Fluctuations in oil prices affect inflation, unemployment, agricultural production, and even the monetary policies of entire nations. Major energy powers, like the United States, Russia, Saudi Arabia, and China, shape their geopolitical strategies based on their energy interests. For many developing countries, fossil fuels represent the only viable source of cheap and constant energy. Renewable energy is still expensive, intermittent, and technically challenging for regions with low investment capacity or fragile electrical grids. Thus, oil and gas remain the backbone of development, even at the cost of Earth's climatic future. Another relevant factor is the consumption pattern and behavior of modern society. From private cars to fast fashion, everything revolves around a fast-paced logic of production, consumption, and disposal. Oil provides the plastic for packaging, synthetic fabrics, machine lubricants, and the energy for transportation. Urban life has been shaped by the idea of rapid mobility, mass production, and constant availability. Even processed foods depend on logistics chains based on petroleum derivatives for transport, preservation, fertilizers, and pesticides. This deep integration creates a cycle of dependence in which oil becomes not just a raw material, but an invisible mediator of the entire modern experience. Geopolitics also fuels this dependence. Access to oil and gas is often treated as a matter of national security. Military conflicts, economic sanctions, strategic alliances, and bilateral agreements revolve around supply routes and energy reserves. Russian gas that supplies Europe, Middle Eastern oil fields, South China Sea reserves, and Brazil's pre-salt layer are all sensitive points on the global chessboard. And while countries seek to secure their energy, investments in fossil fuels continue, even under the discourse of a green transition. Advertising and lobbying by the oil and gas industry also play a major role. Large corporations invest billions to influence public policy, fund favorable studies, and maintain the image of their products as necessary and unavoidable. For decades, well-crafted campaigns have downplayed the climate effects of fossil fuels, sowed doubt about scientific consensus, and promoted ideas like more efficient cars or clean natural gas, diverting attention from the real urgency, the progressive elimination of carbon combustion. This narrative still dominates much of public opinion and consumer choices. Even with these obstacles, changes are underway. The drop in the cost of solar and wind energy, the rise of electric vehicles, advancements in energy storage, and the development of green hydrogen show that fossil dependency can be overcome. But for this to happen in a fair and effective way, a coordinated plan is needed, uniting governments, the private sector, civil society, and the scientific community. The transition will not be automatic or fast. It will require deep changes in how we live, produce, and consume. Today's dependence on oil and gas is not just a legacy of the past. It is a daily choice we make as a society. And until we break this cycle, we will continue feeding a machine that warms the planet, depletes resources, and endangers future generations. The technology exists, the knowledge exists. What is often lacking is the collective decision to change. At the heart of the global energy and climate crisis, a quiet yet powerful hope emerges: renewable energy. Unlike fossil fuels, which take millions of years to form and leave behind a trail of environmental destruction, renewable sources are based on continuous and inexhaustible natural flows. The sun that rises each day, the wind that blows without end, the flowing rivers, the heat from the Earth's core, and the life cycles of biomass. These energy forms not only offer a technical alternative to oil, gas, and coal, but also propose a new relationship between humanity and nature, a relationship grounded in balance, sustainable abundance, and respect for the planet's limits. Solar energy is perhaps the most promising of all. In just 1 hour, the sun delivers more energy to Earth than humanity consumes in an entire year. Photovoltaic technologies, which convert sunlight directly into electricity, have developed exponentially over recent decades. Installation costs have fallen by more than 80% since 2010, making solar power competitive, or even cheaper than fossil fuels, in many parts of the world. Solar plants range from small residential systems to massive solar parks like the Noor complex in Morocco or the Tenga Desert Solar Park in China, with thousands of panels stretching for kilometers. Solar energy is silent, scalable, low maintenance, and above all, clean. Wind energy, driven by air currents, has also gained significant ground. Next-generation turbines now exceed 150 meters in height, with blades capable of harnessing even the faintest steady breeze. Coastal areas, plateaus, and open plains are ideal for installing these silent giants. In regions with constant wind, generation is reliable and maintenance is relatively simple. Today, countries like Denmark, Spain, Germany, and Brazil already supply a significant share of their electricity matrix with wind. Offshore projects, turbines installed in the sea, are expanding rapidly, harnessing ocean winds and reducing visual impact on land. Hydropower, on the other hand, is a well-established force. By damming rivers and channeling water through turbines, it efficiently converts kinetic energy into electricity. In countries with abundant rivers like Brazil, Canada, Norway, and China, hydropower accounts for a substantial portion of electricity production. However, while renewable, hydroelectric energy is not impact-free. Large dams disrupt ecosystems, flood forests, displace riverside communities, and interfere with sediment cycles. Thus, new approaches are being adopted, such as small hydropower plants and river turbines, which minimize the large-scale environmental damage caused by traditional dams. Geothermal energy harnesses heat from within the earth to produce electricity or provide heating. In regions with volcanic activity or tectonic fault lines, such as Iceland, Indonesia, the Philippines, and parts of the United States, this resource is abundant and highly efficient. By drilling geothermal wells and injecting water that returns as steam, turbines can be powered reliably. Geothermal energy is constant, predictable, and has a near-zero carbon footprint. The challenge, however, lies in its geographic limitations and the high initial costs of drilling and infrastructure. Biomass is another renewable source, derived from burning or fermenting organic materials, such as agricultural waste, manure, wood, and energy crops, to produce heat, gas, or electricity. When managed sustainably, biomass can be carbon neutral, as the CO2 released during combustion equals what was absorbed during plant growth. Moreover, it provides a solution for treating solid urban and rural waste, transforming garbage into usable energy. In countries like Sweden, Finland, and India, biomass plants play a strategic role in the energy matrix. However, poor management, such as deforestation for monoculture energy crops, can lead to more environmental harm than benefit. One of the major challenges of renewables is their intermittency. The sun doesn't shine at night, the wind doesn't always blow, and river flow varies with the seasons. Therefore, the development of energy storage systems, such as lithium-ion batteries, hydrogen storage, and thermal storage, is essential to ensure a continuous supply. Smart grids are being developed to balance supply and demand in real time, enabling multiple renewable sources to operate in an integrated, reliable, and stable manner. In addition, the growth of renewables requires investments in education, infrastructure, public policy, and scientific research. The energy transition is not just a technological shift, it's a paradigm change. It involves consumption habits, urban planning, land use strategies, and social justice. For clean energy to benefit everyone, access, equity, and sustainability must be ensured at every level of the chain, from producers to end users. The future of energy, contrary to popular belief, will not be powered by a single miracle source. It will be built on a diverse, decentralized and intelligent matrix, where each renewable source plays a complementary role. The energy of the sun, the wind, the water, the earth, and life itself not only offers us a technical escape from the fossil crisis, it invites us to rethink what it means to live in harmony with the planet. Abundance is within our reach. The choice is in our hands. Among all modern energy sources, nuclear energy holds a peculiar position, at once promising and feared, efficient and controversial, capable of powering entire cities with minimal emissions, yet also capable of triggering irreversible environmental catastrophes. Since its inception in the mid-20th century, atomic energy has divided opinions, carrying both the stigma of the Hiroshima and Nagasaki bombs and the hope of a clean, abundant solution for humanity's energy future. To fully understand it, one must explore its physical foundations, benefits, risks, and limitations. Nuclear energy is produced through the process of nuclear fission, in which uranium-235 or plutonium-239 atoms are bombarded by neutrons, breaking into smaller nuclei and releasing a colossal amount of energy. This thermal energy heats water, generating steam that turns turbines and produces electricity. The process is highly efficient. A single gram of uranium can yield the same energy as tons of coal or oil. Moreover, nuclear power plant operations do not emit carbon dioxide, methane, or other greenhouse gases, making them, in theory, a low-emission energy source. Today, countries like France, the United States, Russia, China, and Canada operate dozens of nuclear reactors. France, for example, obtains about 70% of its electricity from nuclear energy. Japan, even after the Fukushima disaster, still maintains part of its energy matrix with reactivated reactors. The technology has evolved over time. Third-generation reactors are safer, more efficient, and designed to withstand human error and natural disasters. Prototypes of small modular reactors, SMRs, promise to democratize access to nuclear power, reducing costs and risks, while fourth-generation reactor technologies, still under development, aim to consume nuclear waste as fuel. However, the risks associated with nuclear energy are real and extremely serious. The Chernobyl disaster in 1986 is the most extreme example. An explosion in reactor number 4 released massive amounts of radiation, contaminating vast areas of Ukraine, Belarus, and Russia. Thousands of people were evacuated, many developed cancer, and an exclusion zone remains uninhabitable to this day. In 2011, the tsunami that struck Japan caused the collapse of the Fukushima Daiichi plant, leading to radioactive leaks into the ocean and soil. These disasters revealed the vulnerability of nuclear plants to human error, technical failures, and extreme natural events. Another major challenge is nuclear waste. The radioactive byproducts of nuclear plants remain hazardous for thousands of years and must be stored safely in geologically stable locations. There is still no global consensus on the definitive disposal of such waste. Some countries use deep underground repositories, others store the waste in temporary facilities near the plants themselves. The risk of leakage, nuclear terrorism, or transport accidents constantly looms over this chain. Furthermore, uranium mining and enrichment also cause significant environmental and geopolitical impacts. There is also the risk of nuclear proliferation. The same technology used to enrich uranium for peaceful purposes can, with small modifications, be used to produce fissile material for nuclear weapons. This makes the spread of nuclear energy a strategic concern for global security. Agencies such as the International Atomic Energy Agency, IAEA, monitor civil and military nuclear activities to prevent diversion. But the dual-use nature of the technology remains a sensitive issue in international diplomacy. Despite all these challenges, many scientists and engineers argue that nuclear energy can and should play a role in the future energy matrix. In aggressive decarbonization scenarios, it emerges as one of the few sources capable of providing large-scale baseload power without relying on the weather. While sun and wind are intermittent, nuclear power can operate continuously, offering a stable foundation for electric grids that integrate multiple renewable sources. Countries with geographic limitations or water scarcity also see atomic energy as a viable alternative. But the decision to invest in nuclear energy is not only technical, it is also political, cultural, and ethical. It involves accepting risks that are low in probability, but immense in impact. It also requires assuming intergenerational responsibility for managing waste that will remain dangerous for millennia. At the same time, it means acknowledging that inaction in the face of climate collapse also comes with immeasurable costs. In a scenario where every solution has pros and cons, nuclear energy stands out as a powerful tool, but one that must be handled with extreme caution, transparency, and scientific rigor. In the end, nuclear energy is neither a perfect savior nor an apocalyptic villain. It is a complex technology, with real potential and legitimate risks, that demands mature collective debate. In an age of climate urgency and the pursuit of clean alternatives, it remains one of the most intensely discussed and perhaps most inevitable options. In the face of the 21st century's complex energy landscape, there is no room for one-size-fits-all solutions or universal formulas. The future of energy will be built on a diverse, flexible, and interconnected network of technologies, where each source plays a specific role and every innovation becomes a step on the ladder of sustainability. This future is neither abstract nor distant. It is already taking shape in laboratories, startups, research centers, and public policies around the world. The goal is not only to find cleaner sources, but to create an intelligent, decentralized, and resilient energy system capable of meeting the demands of a growing population without exceeding the planet's limits. Among the most promising technologies is green hydrogen. produced through the electrolysis of water using electricity from renewable sources. Unlike grey or blue hydrogen, which are derived from natural gas, green hydrogen emits no carbon at any stage of its production. It can be stored, transported, and used as fuel in vehicles, industries, and even electricity generation. Countries like Germany, Japan, Australia, and Chile are heavily investing in green hydrogen production hubs, envisioning a future where this versatile element replaces fossil fuels in hard-to-electrify industrial applications. Another major breakthrough is nuclear fusion, a technology that seeks to replicate the energy generation process of stars. By fusing light atoms such as hydrogen at extreme temperatures, an enormous amount of energy is released with minimal radioactive waste. Unlike fission, fusion carries no risk of catastrophic meltdown and does not produce long-lasting nuclear waste. Projects like ITER in France and private ventures such as Helion and TEI Technologies in the United States aim to make fusion viable in the coming decades. Although it still faces enormous technical challenges, fusion represents one of humanity's greatest hopes for clean, virtually unlimited energy. Next-generation batteries are also critical for making the energy transition viable. Beyond lithium-ion batteries, technologies such as solid-state, redox flow, sodium and metal-air batteries are being developed to deliver greater energy density, improved safety, and reduced environmental impact. Efficient energy storage is essential to offset the intermittency of renewable sources and ensure stable supply. At the same time, thermal storage, pumped hydro and gravitational energy systems are being improved to offer long-duration and cost-effective alternatives. Another key axis of the energy revolution is the development of smart grids, which can integrate multiple energy sources, monitor real-time consumption, and dynamically balance the load. These networks use sensors, algorithms, and artificial intelligence to prevent overloads, detect faults, and optimize electricity use. In connected cities, residential solar panels, electric vehicles, home batteries, and intelligent buildings interact with the grid as small autonomous nodes, creating a distributed energy mesh that is more secure and democratic. Energy efficiency will also be a fundamental pillar of the future. Rather than just generating more power, the new paradigm is to use what we have more wisely. Passive buildings with advanced insulation, natural lighting, and optimized ventilation can drastically reduce energy use. Ultra-efficient electronics, LED lighting, smart inverter motors, and AI-controlled heating and cooling systems are already part of everyday life in pioneering countries. Industry 4.0, with digitized and optimized processes, also reduces energy waste on a large scale. The cities of the future will be central to this transformation. Urban centers account for over 70% of global energy consumption and concentrate the main challenges and opportunities of the transition. Smart cities with electric public transport, cycling infrastructure, green buildings, and sustainable urban planning have the potential to significantly reduce energy demand and emissions. The concept of the 15-minute city, where everything a person needs is accessible by foot or bike, represents a paradigm shift in the relationship between urbanism, energy, and quality of life. But the energy future will not be built on technology alone. It requires political will, international cooperation, social inclusion, and cultural transformation. Clear public policies, ambitious goals, and accessible financing are essential to accelerate the transition, especially in developing countries. Energy equity, ensuring everyone has safe, clean, and affordable access to energy, is one of the pillars of climate justice. Without it, any progress risks deepening inequality and concentrating the benefits of the transition in just a few hands. Education and collective awareness also play a vital role. Informed consumers demand more sustainable products, pressure governments, and adopt responsible energy habits. Every daily choice, from how we travel to how we cook or light our homes, is a silent vote for the kind of energy system we want to build. The energy transition is not a single event. It is a continuous process that depends on each of us. The energy future will inevitably be the result of a combination of technical innovations, political decisions, environmental responsibility, and cooperation among nations. Moving in that direction is not just a matter of development, it is a matter of survival and legacy. Over hundreds of thousands of years, humanity has learned to shape nature in its image, extracting from it food, shelter, warmth, and ultimately, energy. But never before has this relationship been so intense, so fast, and so risky as in the past 2 centuries. Our dependence on fossil fuels, coal, oil, and natural gas has brought comfort, development, and progress, but it has also led us to an existential crossroads. What began as a liberating discovery has gradually become an invisible trap. The more we feed on fossil energy, the more we compromise the very foundations that sustain life on Earth. The carbon era brought light to cities, speed to roads, and connectivity across continents, but also smoke to the skies, heat to the oceans, and imbalance to the climate. What we face today is a planet that is exhausted, overheated, and destabilized. The atmosphere holds more greenhouse gases than at any other time in the past 800,000 years. Polar ice is melting, forests are shrinking, and oceans are acidifying. And behind every alarming graph are human stories, displaced communities, threatened cultures, lives lost in increasingly frequent climate disasters. What once seemed far away is now at our doorstep, and although science has clearly identified the causes, namely the unchecked burning of fossil fuels, the challenge now is political, economic, ethical, and deeply collective. The time for hesitation has run out. What remains is the choice. The alternatives are already here. Every day, the planet offers us abundant and clean energy. In the sunlight, in the dancing wind, in the flow of rivers, in the heat of the earth, and in the ongoing renewal of plant life. The technologies to capture, store, and distribute this energy are more accessible and effective than ever. Countries, cities, communities and companies are proving that it is possible to build a new energy model, cleaner, fairer, more resilient. But this transition will not happen on its own. It requires political courage, investment in research, environmental education, industrial innovation, and above all, social will. It demands that every citizen, every government, and every organization acknowledge both their share of responsibility and their power to bring change. The climate crisis is, above all, a reflection of the imbalance between our technical intelligence and our ecological wisdom. We are capable of moving tons with a touch, crossing oceans in hours, and creating networks that connect billions. Yet we still hesitate to let go of an energy model that clearly leads us toward collapse. This contradiction is the dilemma of our time. We have the means, but not yet the will. The will to stop investing in destruction and begin investing in regeneration. The will to replace greed with cooperation, exploitation with renewal, and fear with hope. As we contemplate the future, the essential question is not whether we have enough technology to change, because we do. The question is whether, as a species, we have the maturity to turn this change into a global pact. The energy we choose tomorrow will be the ground on which future generations either flourish or wither. The kind of energy matrix we sustain today will reflect the kind of society we aspire to build. One that perpetuates scarcity, inequality, and destruction, or one that embraces intelligent abundance, intergenerational solidarity, and a deep reverence for life. There are no easy answers nor comfortable shortcuts, but there are possible paths, and some have already begun to be forged. It is up to us to decide whether we will expand or abandon them. The energy transition is not merely a technical or economic task. At its core, it is a civilizational choice. And in that choice, we will define not only the source of our light, but the nature of our shadow. The future will be the reflection of the decisions we make today. And between a livable planet and a wounded one, between regeneration and collapse, the difference may quite literally lie in the switch we choose to flip.